Hi, good afternoon. Do you hear me well? How is the audio? Okay, cool. Okay, one more minute, we can start. Okay, it's 3 already, so we can start. So, hi everyone, and welcome to the Probability Theory Crash Course. I'm Borisov, one of the TAs for the course. And yes, I'm going to go through some of the course material and help you prepare for the exam. Yeah. The slides are largely adopted by our professor Max Heaney. So for a total of 6 lectures, I'm going to go through the materials, give some examples, and then also discuss some common problems that I saw in the homework, some things that are pretty common to make mistake on. And also in between, I'm going to give you some tips on how to answer better so you can get a bigger score on your on your questions. And feel free to ask questions in the chat, and yeah, whenever possible I will address you for that. Okay. So these are the topics that we are going to cover today. This is the 6 lectures of the course. So the probability, combinatorics, variables, Bayes theorem. Yeah. Okay, so the first part is we start from lecture 1 with more or less the definition of probability. Is where you have so you have the state of events, of all possible events, and then you care about something that you would call beneficial outcomes or successes or something like that. So you divide this space into the things that you care about and the things that are not so interesting, and then you want to find the probability of the things that you care about. So like coin tosses or dice falling on certain pips, or a hand in poker or anything like that. And if you have like very simple examples, then you can compute. The easiest way to compute that n and m is with combinatorics. Okay, so we have 4 types of sampling based on whether it's ordered, unordered, with and without replacement. So the difference between ordered and unordered is when you have, of course, like whether you care about the order or not. So if you want to make groups of people, for example, you want to you have 20 students and you want to make groups of 3 people, then you don't care about the order. So like Borislav, John, and Marta is the same as Marta, John, and Borislav. But in some cases you want to you care about the order. So for example, you want to see how many ways these people can divide first, second, and third place on some programming hackathon, for example. Yeah, and with and without replacement, you always have to reason whether you can have multiple copies of this thing and whether you put it back. So usually with people you cannot do replacement because you cannot have 2 copies of Borislav in the same place. But with other examples you can. So the easiest part is actually to fill in the formula. The harder part is actually to reason about which one of this is which of this is the case. So and there's not exactly any like rule of thumb or something like that which will tell you exactly which one is it. So you have to sort of get in the practice of reasoning which one do you think is unordered, which one is ordered, and with and without replacement. So here I give you three quick questions, and maybe you can spend like a little bit, like 1 minute to think about this. Which one do you think is ordered, unordered, with, without replacement? You can also post your ideas in the chat if you're ready. Okay, so yeah, the first one is unordered without replacement. We cannot replace people, and we just like form, yeah, just any group. Yeah, that makes sense. Yeah, this one is ordered. Mhm. And the third one's a bit trickier. Yeah, so for the third one, yeah, in the first two, I sort of prime you into this idea that people are the thing that is being placed onto. But in the third example, you can see that actually the hotels are, yeah, it's unordered with replacement, because this time the hotel is the one that is being sampled on. So think about it like this. 10, 9, 8, 7, 6. So we fill it in this formula, and then we get, so n would be n is 5 and k is 10. So this would be 14, 14 choose 10. So to be 14 times 13 times 14 times 13 times 12 times 11 divided by 1 to divided by, is it 4 factorial? 5 factorial, yeah. Yeah, sorry I didn't like prepare the answer, it's just the basic logic of how do you pick which formula is it. So n is the bins in which you put the stuff, and k is your samples. Okay. Yeah, I think this is mostly for lecture 1. I think most of the works were pretty good. At least the people. Why is this one with replacement? Because you have you can pick. You are replacing the hotels basically. You're not replacing the people, but the hotels. So you can have sort of like copies of the hotel that are assigned to different people. I'll explain this. You have sort of 5 bins. No, you have 10 people, and then for everyone you have to relocate a hotel. But then you can have the same hotel to be applied to several people. I can send my slides to a cognac for them to send it to you. Yeah, because multiple people can go to the same hotel. Yeah. You're sort of placing the hotel in the people bin. One, the other one was in the other two examples you place the people in spots. And it's kind of the inverse idea. Yeah. Yeah, so are there any more questions about this ordered, unordered, with and without replacement? I think most people did quite well on this homework. So yeah, maybe you'll be fine without. Okay, if there's no more question, I'll continue with the next topic. It should be the axioms of probability and like the general rules that you can use probability. And very important, the base rule. So before we discussed the probability of single events, and now I can introduce the concept of joint probability. This would be two events happening at the same time. So you throw two dice, what is the probability that both of them are even? Or you throw two coins, what's the probability that both of them are heads? Yeah, what's the probability that it will both rain and be sunny, so you get a rainbow? These kind of things. And then you have the conditional probability, which will be you sort of take the whole joint probability, but then you already know that one of the event is happening. So given that you know something, then you can change your probability of what A is. So given that you know B, this somehow changes your probability of A if they are related. So basically that's a conditional probability. What is it stating? And these first two come directly from the axioms of probability. And base rule directly comes from the rule of conditional probability. So if you put this P, the joint probability of A and B on one side, you can see that this is equal to both of these expressions. So in joint probability, P of AB will be equal to P of BA. In conditional, it's not they're not homogeneous, so you cannot interchange A and B. And from that rule, you can directly derive Bayesian base rule. And base rule is generally used to have, so if you observe some evidence, how can you change the probability of the belief of the hypothesis that you're thinking about. Okay, so maybe it's a bit easier if I show an example. So in this example, we have someone with a rare disease that afflicts only 1% of the population. And when John is tested, he is positive. So we have the the test identifies positive cases correctly 98 out of 100 times and accurately identifies 95% of the negative cases. So here the question is, what is the probability that John has lizard foo? So here we have the first step when you solve this, the base rule example, is to derive, to look at the numbers and try to derive as much as possible from to formalize it. So in that case, we can see here we have 1% of the population, we have positive cases, and we have the correctly identifying a negative case. So let's say the probability of L we have the probability of L, where L is being infected with lizard flu, is 1%. Then the next will be, given that we know, so given that the person already is infected with the flu, then the probability that test will be positive is 98%. So you can take that from this sentence. So given that you are positive, the test will correctly find in 98% of the cases, and accurately identifies 95% of the negative cases. So that will be, if you know that you don't have it, then the test will be negative with 0.95% probability. Another question is, so given that we know the test is positive, what is the probability that John has the lizard flu? And this is, so from here we can directly apply base rule. So that will be yeah, so we have the likelihood, and we have the base rate of infection, which is divided by the probability of being positive. And then this is the PT, the probability of the test being positive. You need to compute the marginal probability over both cases. Okay, and once you identify the numbers, this is the most important step. Then you can just fill that in the formula. So for base rule, it's one of the core topics, so you can expect to sure that there will be some problem like that on the exam, because this is very important for probability theory. And one common mistake that I find in a lot of homeworks is that when you compute the marginal probability, so this is the one, the denominator in the when you compute base rule. So some people are taking A and not A, even if you have A to be multiple, to have many cases. So the example was with I think with the defective devices from mobile phones. So you always need to sum up over all possible cases. You cannot group cases together. So if you have if your AO is not a binary variable, it's a tetrary variable or with 4 states, then you need to have 4 of these expressions here. You cannot group because then it will depend on what exactly you're testing, and the marginal probability never depends on that. Okay. Are there any questions on Bayes theorem, Bayes rule? Okay, then I can continue with the next topic in the same lecture, the independence. So here I also saw a lot of confusion in the homeworks. So you have two events. You have two events A and B, and you want to check if they are independent. Marginal probability. This is the definition of marginal probability. So you have some event B, and then this is if you know the different conditional probabilities of that event, you need to sum up over all possible states of A to get the marginal probability. Because sometimes you don't know exactly the probability of B. No, this is part of this is the denominator in Bayes rule. Okay, so I can continue with independence. We have two events A and B. So we are interested whether these two events are somehow related. If one other event can tell us something about the other event or not. And yeah, this is very useful property that will come up often in later when discuss probability theory. So it's not enough to compute just PA and PB and just put it in the equation. You need to compute so the joint probability, and the probability of every single event separately. So you compute these three separately, and then you check if the equality holds. If the equality holds, then they're independent. If it doesn't, then they're not independent. Yeah, so that's very important. And if you don't know that they're independent, you cannot just say that A times PB is equal to the joint probability of A and B. You need to know first that they're independent. And yeah, in some cases, we can reason about independence. So here I'm going to use one of the examples in the homework to discuss like how we can reason about independence. So you should be all familiar with this question. Yes, it's independent if it's true. So if it holds, so if this holds, then basically knowing A or B doesn't give you any information about the other one. You can think of it like that, because if if they had some overlap, then that joint probability will be less. Yeah, that's true. You can use that formula to, if you don't know the independence. Yeah, but often you also don't know the disjoint probability. Yeah, if you also can prove that the overlap between A and B is 0, then it also works. Yeah. Okay, we can continue with this example. Yes, you should all be familiar with this question. So we have every participant has either shoplifted or not, and they receive randomly drawn cards which say have you ever shoplifted or have you never shoplifted, and then the answer yes or no. So here it's very common. Very commonly, people start writing that have you ever shoplifted and yes or no are independent, and just multiply these two probabilities, which is actually not the case. So if you formalize it like that, you have the probability of a person answer yes, the person has shoplifted, or the probability of getting a card. Then you can see that some of these are dependent, some of these are independent. So when you think about it, if you get this card, imagine you get a card that says, have you ever shoplifted? Then your answer is basically determined by the card that you get, because you already know that you have or you haven't shoplifted. So there's no randomness. Once you get the card, you have to answer either yes or no. That's why they are not independent, and you cannot just multiply them together to get a joint probability. But if you have something like shoplifted and ever, then you can be certain that they are independent. Because, so let's say you shoplifted in the past, or you have never shoplifted, this in no way can influence you drawing random cards. Right? So yeah, I'm not going to give you the answer to this thing, but the trick is to actually express the probability of saying yes as have you shoplifted ever, have you never shoplifted never. So that's the idea, because if you do yes and ever, then you know they are not independent, so you don't know what is their joint probability. While for shoplifted and ever, you can use directly the joint probability, and then also separate into two different parts. So you have the probability of yes will be equal to shoplifting times the probability of ever plus not shoplifting times you get a card of the probability of getting a card never. Okay. Ooh, I have empty slides. Okay, so this, I think this covers base rule and independence. If you need to find a pairwise independence, then you need to prove all pairwise connections between three variables. So this is also something that you should be familiar with from the homework. So if you have A, B, and C, and to check if they are all independent, then you have to find for every combination. So basically just do this 3 times for every pair, and then do it 1 time for all of them. So P A B C should be equal to PA times PB times PC. You can also expect something like this on the exam. Something that requires you to reason about independence and compute something with it. Are there any questions on independence? On proving independence or reasoning about what two events are independent? Okay, if not, we can continue with the next topic, which is random variables and probability distributions. How would I reason about it? Yeah. So you have to think about, is it possible that these two things are somehow related? It really depends on the question that you are posed with. So let's see what kind of example to give. Uh, so if you can get these three values, then you don't need to reason about it. You can just prove it. So if it's possible to compute these three values, then yeah, there's no need to reason about it. You can just compute it and prove that is the case. But for example, here you don't have access to the joint probability. If it's related, it's dependent. If knowing one can give you some information about the other or the other way around, then they are somehow dependent. Yeah, it's what kind of example to give? For example, socioeconomic status and smoking. Do you think they are dependent or independent? Yeah, I also think so. Not, yeah. Yeah, typically people that are rich, that are much richer, live healthier than middle class or poor people. Yeah, so there's some dependence. Even though it's hard to say, like, if you earn 2,000 euros, does it mean that you smoke? It's not that easy, but yeah, statistically there should be some some kind of difference. For example, if you put two people into groups and say like one is above 3,000, the other one is below 3,000, you can guess that there will be some difference in the probability of the smokers. Yeah. Yeah, and if you get some kind of question like this on the exam, you have to think about it like this. Can you say something about one variable if you know the other? Even if you're not certain, just if it gives you some information, then there could be dependent. Yeah. Okay, if it's all clear, then we can move on to the random variables and probability distributions. Yeah, so a random variable is any value that depends on just some random process. So yeah, there are a lot of examples. We typically use the coin tosses, dice, but it's pretty much everything from daily stock prices, weather. Yeah, there's many random processes all around us, and everything can be sort of quantified by some variable x with some specific probability distribution. Okay, I phrased that wrongly. Sometimes it's not very clear what kind of probability distribution you're using, but in the cases we are going to cover, it's going to be one of the things that we studied. Sometimes you need like to build a whole model of probabilities, but this you learn that later in your study. So the most common probability distributions that you can expect are uniform, Bernoulli, binomial, Poisson, and the Gaussian distribution. So in the uniform distribution, you have everything is equiprobable. So all the outcomes are equally likely within the range of the uniform distribution. And the uniform distribution can be either categorical or continuous. So you can have discrete events like throwing a dice, or you could also have continuous events like I don't know about an example for continuous uniform distribution. So then for Bernoulli trial, you always have a binary event, and you are interested in a single trial of that binary event. So it could be single coin toss, yes or no question. I give, for example, here whether it's going to snow or not today. So this is a single trial. And then you have the binomial distribution, which is practically you repeat Bernoulli trial many times, n times, and then you're interested in the number of successes. So you're not interested in the order in which they appear. You're just interested in exactly how many times they will occur. So if I throw a coin 1,000 times, is it going to fall 600 times on the same side? Poisson distribution is also somehow related to binomial, but it's typically used for something that has a low rate of probability. So you have many samples. In most of the samples, nothing happens, and then occasionally you have you have some positive case. And Poisson also can approximate binomial distribution in this, in very in these cases where binomial distribution has low probability for the success. So this Bernoulli binomial and Poisson are necessarily discrete because you only have yes or no, like binary events. While the normal distribution is a continuous distribution. So there you don't have discrete, there you have just continuously going from different values. And this is characterized by the mean and the standard deviation. Okay. So in this lecture we also talk about the probability mass function. So before we talk about probabilities, so the probability of a given variable, and our probability mass function is a function that maps from every possible state to every probability. And the unique property of the probability mass function is that all probabilities need to sum up to 1. So this is very important to use, and yeah, it's quite possible that you have something like this, that you have to use something like that on the exam. You have to use this property that probability mass function equals to 1 to discover something. So here I give an example with a card game where we have so we have all cards from 2 to 10 have their respective score, and then Jack, Queen, and King also have a score of 10. Your ace counts for 11. So now we have a random variable that represents the value of the next card that you're going to draw. And you have to determine the probability mass function of the score. So how would you do that? Maybe think for a second, for like spend some time thinking about it. It should be a trivial example. Okay, so we can count no, it's actually not uniform because you have 4 cards that have the same score. So uniform would be if you have if you're interested in what card are you drawing exactly. But in this case you have the Jack, Queen, and the King and the 10 all have the same score. So then the probability mass function will actually be weighted by for the values of x being equal to 10. So if you have so x here will be the score of a single card, not the card itself. If you have the card itself, then it's uniform. You should be also familiar with this problem from the homework. we had something similar except with the dice. Okay. So now I can move on something a bit more complicated, the binomial and the Poisson distribution. So this example from the lecture slides that we used. So say we have the probability of death by lightning is 1 in 500 million, and we have 17 million people. What's the probability that you get 3 or more hits, 3 or more deaths by lightning in 1 year? Maybe it should be 2021 now, because we already know how many of them occur in 2020. So with binomial distribution here, yes. So if you need to give a probability mass function, you need to list possible outcomes. So if it's something long and you can shorten it like this, like a function, it's fine. Or if it's easier for you, you can also just list all the values. So just say p1 equal to something, p2 equal to something, p3 equal to something. It depends on the question. Yeah. Yeah. So there's some delay between me saying something and you receiving the stream. That's why I'm a bit slow to react to the questions. Yeah. Okay, so when we have this sort of problem, we're interested in okay, so first thing is we have a person either dies or doesn't die by lightning, which is a binary event, which means that we can model it with binomial, and it's also rare enough to be modeled by Poisson distribution. So what we're interested here is first identifying what are the so we have the probability, the number of samples, and how many times we're interested in the event for binomial distribution. So this will be n, p, and k. And for Poisson distribution, we're interested in lambda. So reading at this, can you think like what is p, what is m, and what are the k's of interest, the k value? Any ideas? You can write in the chat. You should be able to like extract from sketch. Okay. Let's see if I cannot. Is that what you mean, to draw something on a board? Okay. Okay, so uh, we have deaths, the probability to die by lightning strike is 1 divided by 500 million. 500 million would be to the power of 8. And then we have 17 million people. And was it 3 or more people? 3 or more. To be struck by lightning. Okay. So for binomial, we have 3 variables that we are interested in: p, n, and k. So that will be, we know the probability. The probability of being struck will be this. N is the number of samples, so this should be the number of people. And k will be some number that is bigger than 3, bigger or equal than 3. But here we can use the complement, so you can actually solve 1 minus k being less than 3. So here in this case we have something like binomial with the probability n and k will be equal to 1 minus the sum from 0k until 2k times as a formula for binomial distribution. That will be, wait, not k here, but I. having I here. And then 1 minus p n minus I. So the formula for the binomial distribution. You should definitely write this thing on your cheat sheet because it's not, yeah. I mean, you can remember it, but it's better to know to hear it in a cheat sheet. And then you can just fill in the values here. So this will be I goes from 0, 1, 2, and you have n is your, so this is n, and this is p. Okay. And if we have Poisson distribution, then we have lambda is the rate. So lambda is the rate of the event. And the rate of the event is n times pi, n times the probability. And yeah, the important part is to fill in, to realize which one are the values, and then just fill in the formula for binomial and for Poisson. Can return to my slides because there I have like prettier version of that. So that will be we identify p, n, and k from the text, and we also know that lambda is equal to the probability of probability times the number of samples. And we fill it in the respective formulas to get the final answer. Yeah, and this formula for the binomial distribution and this for the Poisson, you can just write it in your cheat sheet. It's not necessary to remember. It's more important to be able to understand the logic of why how do you get the probability, how do you get the how to use the complement, what is n, this kind of thing is the reasoning behind it. Otherwise, just plugging in the formula is the sort of the less important part, I would say. Whether in the exam, does it matter whether we use binomial or Poisson? So if we ask for exact, then it should be binomial. If we ask for approximate, then it should be Poisson. Or if we specifically say use the rate or use the probability and the samples. Yeah. I think the question will be formulated so it wouldn't be ambiguous which one to use. Yeah. Okay. Okay, and the final topic of the third lecture was how to convert from the probability density function to a cumulative density function. So that's actually quite the easy process, and there's like pretty much not much probability theory, because you just find the integral of the probability to get the you just find the integral of the probability density function to get the cumulative density function. It's not much more than that. And also you can use the fact that once you sum all the possible states, so you have the cumulative distribution just finishes at 1, because the probability of 1 will be including every possible state in your state space. So then this must be equal to 1, and you can use that to find out the constant that you have from integration. I think here most of you also got that correct. Yeah. Okay, so I'm going to stop with the new material for a second and just give you some idea of how we can frame answers such that you can get like more points. So generally, I also try to convey that when I was giving feedback on the homeworks, that if you just write a number like this, it's not very clear if you actually understand it, or you just heard it from someone else, or it's just if you just write an equation like that, it's not clear what you understand exactly from this problem, and whether you'll be able to solve other problems like that. And it's even worse if you have some numerical mistake. Then we have no way of verifying that you know what you're doing, basically. So basically, if you just give answer like this, it's hard to give you like more than half of the points. And if this is long, if this is a long equation and you have one numerical mistake, or you substituted something wrong, then we cannot give any points because we don't know like where do the numbers come from. So that's why I'm saying this is bad answer even though it's correct, and this one is even worse because it doesn't even get the right value. And what a good answer will be to actually try to explain what is your reasoning behind this thing. So you don't need to write an essay about it, but just like with 1 or 2 sentences, explain like what is the distribution, what is the value, what is the random variable, what do you need to compute, and then it's much clearer that you understand what you're doing. And even if you make a mistake in the calculations, you can still get most of the points, because we don't like strictly care about like getting the algebra right. We care about understanding of probability theory. So yeah, that's why I always recommend to have to write a little bit of text to explain your reasoning on the exam. And it's also a good practice to do that for reports and other things later. Okay, so we've already been going on for 1 hour. Maybe you want a short break for about 10 minutes? Before we move on the next topic. Is that okay? Okay, cool. Okay, so let's say now it's 16:07. I wouldn't say it's pretty extensive to say that you're just using uniform distribution or binomial distribution or something like that. Yeah. Maybe this is a little bit more elaborate. I can accept a little bit shorter answer for full points, but it's a good idea to mention what is the distribution that you're using, yeah, before you actually do the computation. Okay. So shall I say we're back at 4:20? Okay. Yeah, I'll just close my camera and open it when I'm ready to start again. Okay, if everyone is back, we can start with the next topic, the expectation and variance. So if we have a random variable, we can summarize some statistics about it. And one of the main interests that we care about is the expectation and the variance. So the expectation would be something like, on average, if you do that infinitely many times, what value do you expect to get from that? So you remember probably that we did some examples with water in the homework. So your expected value was how much money can you earn from playing the water. You just buy tickets all the time and then eventually you win. How much money you can, what is your expected value over the really long term? And you saw with all the casino and the water examples, you always get a negative value because of, yeah, that's how like all the water and the casino people make money. Because of our long period of time, you always get to the expectation. And what defines like how fast you go to the expectation is the variance. So the variance is how much you're going to go up and down before you actually settle on that. Sort of like how many samples do you need to actually go closer to the expectation. And yeah, mathematically the expectation is for every state of the variable you multiply to the probability and you sum up all this together. So the example with the casino was like, so if you can win 5 euro with probability of 20% and then 100 euros with probability of 1%, you can just multiply and add this together, and then also consider the probability that you wouldn't win anything with the complement of these two. And so you use a sum for if it's a categorical distribution, but if you have continuous, then use the integral. So they're sort of identical concepts. The difference is you have categorical and here you have the continuous distribution. Yeah, so we can take one example with a probability mass function that we already computed, and now we can compute the expected value of that. So the expected value of x for this distribution that we have. Now we can start drawing again. So we have 4 divided by 13 if x is equal to 10 and we have 1/13 otherwise. So now our expected value e of x will be equal to the sum of sum over x, where you multiply the probability of x times the value of x. So now we have 1. So if x is 10, we have a probability of 4/13, and it fixes 2, 3, 4, and so on until 9 and 11. So we're skipping only 10. You have a probability of 1/13. So this will be for every possible value of x, you multiply it with a sum, and then you compute the value of this as a concrete number, and this will be your expected value. So this will be 40/13. Some trick way to compute this would be 11 times 12 by 2. Oh yeah, of course, this is 55. So this is 10 plus 1. You put the 1 here, so you have the sum of 1 to 10, which is 55. 55 times 13. I should pick some examples with prettier numbers. 95 divided by 13. So that's the expected score that we are going to get from drawing a card. Okay. Switch back to presentation. Yeah, so here we determine a value, and yeah, that's pretty much it about the expectation. Yeah. So you can also expect something related to expectation and variance on the exam. So you have some kind of probability function, and you need to compute its expectancy and its variance. So variance is a bit more involved, but you can sort of use the same. You use the definition of expectancy to compute the variance. And yeah, again, you can use these formulas in your cheat sheet, so you don't have to remember them. And yeah, so you usually first compute the expected value. So here you can already square it. And here, when you compute the e of x squared, it's very important that you only square the value and not the probability. Okay, so I'm going to show it here again on the board how to do that. Okay, so now we want to compute the variance of the same thing. This will be equal to e x squared minus EX squared. So here the square is whacked on the whole thing. And this, it's actually the sum over x of px times x squared. So this is very important that the probability here is not squared. This was very common mistake in the homework. So when you have expectation of some value, you put a p of x here, because p of x is still your random variable. And another way to think about it is, so x is basically defined for the range of 2 to 11. Right? So then if you plug in, if you say p x squared, and then x is 10, then I have p, the probability of getting 100. But whereas that is not defined, because x only ranges from, the value that you can plug in here only ranges from 2 to 11. That's why you cannot plug in the square here. Okay. And then you have minus this, the expectation squared. Okay, and this, we can use the same. Actually, this I'll just leave it like that, because it seems a lot of computation to estimate this. But you know, the general form will be 2 squared times 1/13 plus 3 times 1/13 plus 4 squared times 1/13, and so on. And the only difference would be for 10. So if you have 10 squared times 4/13. Okay, is this clear? Is this okay? Yeah, okay. Variance, expectation. Good. Okay, I think this, so far, maybe this one is for about at least a 6, if not more, on the exam. So if you know all this stuff, you can get somewhere between 6 and an 8, I guess. Yeah, this I already mentioned this. You cannot square inside the p of x. This was a very common mistake, and yeah, you can be careful of that. So the first 4 lectures is the sort of like the core probability theory, and yeah, this should be enough to pass. And for the next part, it becomes a little bit more difficult, and Is everything clear so far before we start with the fifth lecture? Okay. Okay, so for the fifth lecture, for the fifth and sixth, the content is like a little bit more dense and more difficult. So I just decided to directly use uh, the slides from the course and just walk you through it, what's happening there. So the idea is to, so I think this lecture has two parts. The first one is the maximum likelihood estimation, and the other one was the transformation of variables. So the basic idea in maximum likelihood is that you have uh, you observe things, you collect your data samples, and then you want to estimate some parameter that actually describes your data. So in the homework, we had something like I think student height. So you just take you go to Rabat University, before coronavirus. You go to Rabat University, you measure like 20 different people, their height, and you want to see how much is the height of the average student in Rabat, for example. That's your idea. Because you don't know directly the mean. The only thing that you know is that you can measure some samples, and then from there infer the mean. So the process of maximum likelihood estimation is basically uh, to retrieve the parameters of the distribution. So before, what we did in the course was you have the parameter, you have like mean and standard deviation, and then you compute some probability, or you have the n and the p and compute the binomial. And here this is the inverse process. Here you have the data, and then you want to estimate the parameters. Yeah, so this is what is happening here. You have some samples from a distribution, and you want to estimate the probability of lambda. Okay, so here we have, so this is what we call the generative process. You have your lambda parameter, and from there you sample your data points. And basically the likelihood of that parameter will be how likely is it for these data points to come from this lambda. So if we go back to the example with the student heights, let's say we decide that our mean, so we use normal distribution, and we decide that our mean is 20 centimeters. And then we go and measure the first person, and then they are 108 centimeters tall. And this immediately means that like our estimate of 20 centimeters was way off, because it's very unlikely if your mean was 20 centimeters to get this kind of sample. Okay, so this is basically the formula that represents that idea that the likelihood of a parameter under the dataset is the same as the probability of generating these data points from the model that uses these parameters. Yeah, and so before we specify that you need to have the independent and identically distributed samples. So because it's independent, then you can use this adjoint probability, and x1, x2, x3, and so forth are independent. So you can just, this will be equal to the probability of xi given lambda times the probability of x2 given lambda, and so on, like that. So this will be the basically the product of the equation for Poisson distribution here. So the general principle will be, you find out what is the distribution that's used, what distribution do you want to model your data with, and then you multiply that distribution with the number of samples that you have. So here in this example we have 10 data points. So we use the formula to, we basically take the product of the probability of every one of these points. So is it clear how do we get from data points and distribution into likelihood? Basically that's the part where you have the probability theory. How you get from data points to likelihood of a parameter. Is it clear, or do you have some questions on that? Okay, I was assume, yeah. Some of them, no, you do the product over probabilities, and then when you take the log, it becomes the sum. Yeah. Maybe. Maybe I can just give you some example from the homework. Would that help you more to just like go over the whole process with one example? Okay. Okay, so we have we have some samples, x, x1 to xn, and they are drawn from Gaussian distribution. Gaussian. So now the first step, would be you have the likelihood of one. You have the likelihood of lambda, not lambda, but you have the likelihood of mu, your parameter, the mean, over your data set. So that will be the product of P given X given mu. So here, here I need to fill in the equation for Gaussian distribution. Gaussian but for example in the exam you can have something else like uniform or Bernoulli binomial, this kind of uniform, like all the other distributions that we covered in the lecture. It could be here, and then have the product of this thing. That is something like 2 pi sigma squared x. And this is over x. Okay, for questions. Okay, so practically this part. So all this thing. This is the probability theory. Probability. I'm trying to spell that, but yeah, okay. This is the probability theory. Everything else below that is actually calculus. Secret, it's calculus. Well, not so secretly, but yeah. So what you actually have here in the next step, you are interested in computing the log likelihood. So typically why we're interested in log likelihood is that because computers don't handle the product of probabilities very well, because it's really easy to get underflow, numerical underflow, and that's why it's everywhere in the literature. When you start like reading papers on machine learning, you see that everywhere it's used the log likelihood. So that's why I want to turn this into, we just want to apply the log. And do we need to go over the full process, everything right out, or do you think you get the idea of the stuff? because for this is mostly just rewriting the product sign. So your second step is finding the log likelihood. Your third step would be, so now you're interested in finding the maximum log likelihood. Maximum log likelihood, MLE. Which is basically finding the derivative and setting it to 0. The same way that we were in calculus on how to find the maximum of a function. So to find the maximum, you find the derivative of log L with respect to your model parameter. And then you set that to 0 to find the critical point. So when if this is your log likelihood, you want to find where the derivative is 0. Here. Okay, so does the multiplication turn into sum? Yes, it turns into sum. So here we have, this is some fraction, some constant, and then you multiply it. So I have the product of this many times over, as much as you have samples. So this is just some constant that's going to be raised to the power of n 2 pi sigma squared to the power of n, where n is the number of samples. And here you have the xp, the exponential, and you can use the rule that when you multiply two exponentials, you can just add their exponent. Or maybe it's just easier like that. So you have 2 to the power of 4 times 2 to the power of 2. And this is equal to 2 to the power of 6. Right? So that's how you turn this product. You can put it in the exponential and make it into a sum. So we over x. And so you have this. In the next step, you take the log likelihood. So this is likelihood. You take log likelihood. This multiplication becomes a plus. And this whole thing becomes some constant that's not relevant for a model parameter. The exponential and the logarithm cancel out. So you have something like this for your log likelihood. Like this. And then when I take the derivative, this part is gone. Here use the chain rule. And then set the derivative to 0. And at the end, what you get, so here when you use a derivative, you get something like this, sum x then you set the derivative to 0, and then you can see from here, so you have a sum over x, and then keep on the signs. Missed a minus somewhere. But yeah, generally the idea is that the mean, when you put it in on the other side of the equation, it will become something like the sum of OX divided by n. Because here in this sum, you are summing the mean n times. So you get something like n times the mean is equal to the sum over OX. Is equal to the sum of OX. And from there you get that the maximum likelihood mean is actually basically the empirical mean. You just take your samples and you mean them. Okay, so to recap all this thing, you find your probability distribution, you do the product over all your samples, log likelihood, and then you use basically the calculus to find the maximum of the log likelihood. And this should always be your parameter, so mu or lambda or something for the distribution. Okay. Let's go back the slides. So this is again the same process. The likelihood, log likelihood, derivative, set derivative to 0, find parameter. This is always So once you follow these steps, if you understand the logic from the steps, then it's just a matter of algebra basically to solve this thing. And here, if you want to prepare for this thing, then you can also try to derive few of this yourself. But the process is more or less the same for everything. Okay, so the second topic is transformation variables. So here we have two different distributions that we want to transform. So I have one probability distribution, but we find it more convenient to actually transform it in a different way. So this sounds super theoretical, but if you remember from the 6th lecture, this has practical applications for random sampling. So the general process here is that you want to, so this is just mathematical proofs, but then the general process of how you do that is you want to express, so you have your probability distribution. So this 3x squared, and then you want to express y in x in terms of y to get the appropriate transformation. So once you express that, you also find the derivative and you fill in the formula. Yeah. So here's an example of how this thing can work. I can transform between two distributions. So yeah, this again like mostly just getting the math right. In your cheat sheet, you can just sort of like outline the steps in which you do this transform. So here have your you set your transformation, and then you derive x expressed in terms of y based on that transform that you're interested in, and then you find the derivative of. So this is basically the expression of x in terms of y, and then you just fill in the values and you get this. So that's the whole idea behind it. Yeah, so this lecture is mostly just math with like slight intuitions about the yes, so the f of x is a probability density function, and y is also a probability density function. So you yeah, it's so as we learned in the last lecture, sometimes it's more convenient to sample from different distributions. So it's useful to be able to convert from one PDF to another PDF. So this is a probability density function, and you can figure out some way to map from that to another probability function. And this process actually, it's very similar to what you study in linear algebra about the transformations. You're probably familiar with the linear transformations, and this concept is actually quite similar to that. Okay, are there more questions about this? So basically what I would recommend is you try to solve some few of these problems and just outline the steps that you do. And once you get all the steps right, then so once you can get all the steps right, it's just a matter of like algebra to compute algebra. And can we do example? Yeah, sure. Okay. Okay. Okay, maybe I can pick the example from my lecture, so I'm sure that things wouldn't get like way too ugly. Because if I just pick some random probability density, it might get really messy. Okay, so this was 3x squared was our PDF, and then our transform is x squared, right? Yeah. Okay, so the first step is find inverse of y. The inverse of y, or in other words, find v of y, which is a function that expresses the value of x as a function of y. So here basically we have this expression y is equal to x squared, and we want to express x in terms of y. Or maybe since we are taking derivatives, it's more convenient to write it like that. Okay. So then the second step will be, so now this is also the v of y that we refer to in the formula. And now what we want to do is to find the derivative of v of y with respect to y, which is 1/2 y minus 1/2. Okay. So find inverse, find derivative. The next step will be fill this in the formula. Fill formula. So the formula is f of y is equal to f of x v y times our derivative. To write a shorthand like this. Okay, so now v of y is this value. I'm just going to use different color. This value, and we plug it in f of x, which is this value, this function. So that will be 3 times oh sorry, I just saw that you offered to do the 5/4. It's, yeah, there's a lot of delay between me saying something and then you receiving it, like 10 seconds or something. So that'll be, this is x here, and then you have the square. So this whole thing is x. in the function. Wait, maybe it's confusing if I cross it out. This is x. Yeah, and then here's the derivative, which is what you compare here, y minus okay, so this is 3/4 times y minus 1 times 1/2 y minus 1/2. This becomes 3/8, and then y minus 3 like this. Okay, let's see if I make a mistake in my calculations. Where did I get? Off. Yes, I made a mistake. This one shouldn't be here. It's this one. One half. This is the derivative, this is the value. So this is what I was supposed to feel for v of y. And this is the derivative of v of y. Yeah, so then this contains wrong. And this will be 3 times y times 1/2 y minus half, which is 3 divided by 2 times y square root, or 1/2. And the fourth step is finding the support. So that will be, let's say your x ranges from 0 to 1. Or no, make it more interesting, 0 to 2. So that will be just fill. To find a support, you fill in the values here. So this is your g of x is equal to x squared. Okay, fourth step, find support. So that will be, the support is G0 and G2. So you're transforming the boundaries by the function that maps from x to y. Where does the 3 come from? It comes from here. So because here you want to substitute f of x, but now plug in vy for the value of x, and our f of x is 3x squared. This is where the 3 comes from. Okay. Okay, so the last thing is the lecture 6. Here is everything clear about the transformations? About the process of transforming variables? Okay. So here the main takeaway from this lecture is the three different types of algorithms that are introduced. The inverse sampling, rejection sampling, and this for the distribution, specific distribution. So for inverse sampling, the main idea is to use basically a transformation trick that we talked about in the previous lecture, to go from from the density of one function to another. Yeah, just like to generally to be able to explain what a step 1 and step 2 do. So not really like implementing Python. Yeah. So for example, this part is basically just what we did in the previous, what we are just doing now. You basically have your f of x, and then you want to transform it into a uniform distribution. Yeah. So inverse sampling is that's where inverse sampling is applied. That's where this transformation variable is applied in inverse sampling. So if you have some question like that, you just need to explain the process and maybe show like one equation, like how do you go from f of x to the inverse, if you have a question like that. You don't need to implement you don't have to explain exactly how it's implemented in Python. So generally this type of question will be more like just to check your understanding of how the process works. So for reverse sampling, the main point is that you're using this transformation of a distribution. That's the main thing that you need to be able to explain, and then how do you derive the inverse. So for rejection sampling, then you want to basically explain this algorithm, how it works. So yeah, I'm not sure how to simplify this further, but the idea is that, so you have one distribution which is difficult to sample, you cannot find the inverse, so you pick another easy distribution. So yeah, something like uniform or normal distribution, something like that. Something that's easy to sample. So GFX is the distribution of choice. This one is the target distribution. And here we want to sample, we want to draw random samples from GFX, and then sample from the uniform distribution from 0 to the value that you get from the previous sample. And the idea is that show the graph. So the idea is to actually sample all these things, but then throw away all the samples that are not inside your target distribution f of x. It's also helpful if you actually draw something like that on the exam. So you have our target distribution, you sample from this one, you sample from the orange one, and then you check if the value that you sample here is actually bigger. If it's more than this, then you accept it because it goes here. If it's larger than this, then you reject it because it's outside the curve. That's the general idea in the algorithm. Yeah. And also, yeah, if you so there could be theoretical questions about, so what is this good for? So inverse sampling only works if you can actually invert the distribution. Rejection sampling also has some sort of limitations, where if you cannot find the right M, then you basically reject a lot of samples. I think the worst example is the worst method that's just discussed is how do you sample, how do you use uniform distribution to sample from normal. And the core idea of this thing is the central limit theorem, where if you sample enough values, if you sample enough values and then you add them together, you're eventually going to go central to the mean. So the idea here will be you sample from uniform and then you add the numbers together, or you average numbers together over several samples. And then the more you do that, the more you get closer to normal distribution. So here I can give you some example, maybe to illustrate this better. To illustrate you how the central limit theorem works, and also how do you sample from that. So imagine we draw coins. Again, we have coins. Yeah, we have a coin, €1, and you toss that coin. So say you toss that coin 10 times, and is equal to 10. So then what do you expect for heads and tails? So you expect around 5 heads, 5 tails. But what you could actually get is completely reasonable that you get something like 6 or even 7 heads. It's not impossible. It's with a small sample, it's quite possible to get something like that. It's also possible to get like 3, 2, something like that. So here you have a coin toss which is uniform. It's 50-50. But as you repeat this multiple times, you get, so on average you get 5 tosses, but then you're also going to get, so let's say this is 5, this is 4, 6. So because the expected value is 5, you get the highest value would be 5 tosses when you repeat this 10 times. And then you repeat this process, for example, 1000 times. So you repeat drawing the 10 times, 1000 times. And then you record this every time. How many heads do you get? And basically what the central limit theorem states is that no matter what was your starting distribution, if you do this for enough n's, you always get a normal distribution at the end. So here you have normal x normal, where x is the number of heads, number of heads in n coin toss. And what we find is generally the bigger this n is, the smoother this becomes, the better it fits to the Gaussian distribution. Okay, and yeah, that's pretty much it. That's how you can use uniform to sample. You can sample from uniform and get a Gaussian distribution. Yeah, so this, I know this topic is quite difficult, the random sampling, but if you don't get it right, it's still, you can still get a pretty good score on the exam. But yeah, this material for 10, I'd say, yeah. So this random sampling and uh, maximum likelihood estimate and function transformations. So do you have any questions on this? Sorry, it took longer than I expected to cover everything. Okay, if it's all clear, I think we can conclude. It was really, yeah, quite a lot of things that we covered. I hope it's actually helpful for the exam. And yeah, good luck on the exam. If you don't have any questions. Yeah, you're welcome. Yeah, you're welcome. I'm glad it was helpful. Yeah. Okay, so yeah, I'm going to end the stream. Thank you for attending and good luck on the exam.